Content in this presentation is covered on pages 200 through 201 of your textbook, and it's meant to help you achieve learning objective number 33, which is to define atmospheric pressure and explain how it's displayed on a weather map. Be sure to skim these pages before watching the video and to read the chapter carefully before attempting the online quizzes. Of the various elements of weather and climate, changes in air pressure are the least perceptible to humans. However, they're very important in producing changes in weather because variations in air pressure generate winds that trigger changes in temperature and humidity. In addition, air pressure is a significant factor in weather forecasting and is closely tied to the other elements of weather, such as temperature, moisture, and wind. In cause and effect relationships. We know that air moves vertically if it's forced over a barrier or if it's warmer and thus more buoyant than the surrounding air. But what causes air to move horizontally? The phenomenon that we call wind. Simply stated, wind is the result of horizontal differences in atmospheric pressure. Air flows from areas of high pressure to areas of low pressure. You may have experienced this phenomenon when opening a can of soda or a beer. When you open the can, the gaseous carbon dioxide that was dissolved in the liquid rushes from the area of high pressure inside the can to the area of lower pressure on the outside. Wind is nature's attempt to balance the inequalities in air pressure. So what is atmospheric pressure? We live at the bottom of the atmosphere, and just as the creatures living at the bottom of the ocean are subject to pressure exerted by water, humans are subject to the pressure exerted by the weight of the atmosphere above. Although we don't generally notice the pressure exerted by the ocean of air all around us, unless we're rapidly ascending or descending in an airplane, for example. It's a substantial amount of weight. We define atmospheric pressure or air pressure as the force per unit area on a surface exerted by the weight of the air above. Average atmospheric pressure at sea level is about 14.7 pounds per square inch. In the metric system, the average atmospheric pressure at sea level is equivalent to the weight of 1 kilogram per centimeter squared. Specifically, a column of air 1 square inch in cross-section measured from sea level to the top of the atmosphere would weigh about 14.7 pounds. So this is roughly the same pressure produced by a 1 square inch column of water 10 meters high. The pressure that air exerts at Earth's surface is much greater than most people realize. For example, the air pressure exerted on the top of a small school desk is greater than 11,000 pounds, or about the weight of a 50-passenger school bus. So why doesn't the desk collapse under the weight of the air above? Simply put, air pressure is exerted in all directions, downward, upward, and sideways. So the air pressure around all sides of the desk is exactly balanced. To describe atmospheric pressure, the National Weather Service uses a unit of force from physics called the Newton. Under average conditions at sea level, the atmosphere exerts a force of 101,325 newtons per square meter. To simplify that large number, the National Weather Service adopted the millibar, which equals 100 newtons per square meter. So the average sea level pressure can more easily be stated as 1,013.25 millibars. And if you look at this figure, it shows you the range of atmospheric pressures that have been recorded on the planet. The highest ever recorded was in Siberia in December. So if you can imagine clear and cold weather, you might imagine 1,084 millibars of pressure. Very, very dense air, very cold air, and very high pressure. The lowest temperature or lowest recorded air pressure is the middle of a tropical storm, a typhoon tip, 870 millibars. So we're not going to see on any assignment any sea level pressures greater than 1084 or lower than about 870. Torricelli was a student of Galileo, and he correctly described the atmosphere as a vast ocean of air exerting pressure on the Earth's surface. So to measure this force, he closed one end of a glass tube, filled it with mercury, and then inverted the tube into a dish of mercury. And he found that the mercury flowed out of the tube until the weight of the column was balanced by the pressure exerted on the surface of the mercury by the air in the dish. In other words, the weight of the mercury in the column is equal to the weight of a similar diameter column of air that extended from the ground to the top of the atmosphere. So Torricelli noted that when air pressure increases, the mercury in the tube rises. Conversely, when air pressure decreases, so does the height of the column. The height of the column then is the measure for air pressure. We talk about inches of mercury sometimes. With some refinements, his mercury barometer remains the standard pressure measuring instrument used today. And because air pressure is measured with a barometer, it's also commonly referred to as barometric pressure. Standard atmospheric pressure at sea level, again, 1,013.25 millibars and 29.92 inches of mercury. The need for a smaller and more portable instrument for measuring atmospheric pressure led to the development of the aneroid barometer. And aneroid just means without liquid. So we don't want to be carrying mercury around every place you go, especially not when you need that open dish to remain lidless. You'd lose your mercury and the readings would be off and the tube might fall over. So rather than use a mercury column held up by air pressure, the aneroid barometer uses a partially emptied metal chamber. That chamber is very sensitive to pressure variations. So changes when it detects a pressure variation, it contracts, compressing as pressure increases and expanding as pressure decreases. So as you can see here in this picture, the face of an aneroid barometer, this is one intended for home use, includes words like fair, change, rain, and stormy. Notice that fair weather corresponds with high pressure readings, whereas rain is associated with low pressures. To predict weather in a local area, the change in air pressure over the past few hours is more important than the current pressure reading. Falling pressure is often associated with the increasing cloudiness and with the possibility of precipitation, whereas rising air pressure generally indicates clearing conditions. And so that's why we study the trend. On your weather station models, you'll see not just the current barometric pressure, but what it was 3 hours ago. So we want to know whether the general trend is towards higher pressure or lower pressure, because that helps us understand what the weather conditions might be in the future. Another advantage of the aneroid barometer is that it can be connected to a recording mechanism. So an instrument like the one in the photograph here is called a barograph. And it makes a continuous record of pressure changes over time. This is a roll of heat-sensitive paper with a hot pen that is leaving a trace of the barometric pressure trends. And you can see when they first put the paper on here, over kind of on the right side of the barrel, the blue line was at about 1010 or 1011 millibars. And by the time we're almost 24 hours, in fact, we're 24, 3, 2, 1, 0. We're about 18 hours later. We can see that the pressure on this recording paper is more like, what is it? 1025. So increasing pressure from 1010, which isn't such bad weather to begin with, but it's in the change to fair on the face of this barometer in the top right corner. All the way up to 1025, things are looking good, right? And that trend is, it's fluctuating a little bit, but it's generally up. So when we look at the barographs, we have a mechanical way to record these things. Of course, these days with computers, we have a much better way of recording data, and we don't really have to use those heat-sensitive pens so much. But this counts as a sort of a standard and permanent record of what the weather conditions were like. We also see the adaptation of a lot of barometers to indicate things like the altitude for aircraft. It can be a direct relationship to topographic elevation, because we know that if we have air pressure of a certain level at sea level, if we climb up the mountains, we're going to be at a lower air pressure. And so we can use an aneroid barometer to tell us when we get to a different elevation. In fact, pressure readings on surface maps are important tools for meteorologists. So to show pressure patterns over Earth's surface, meteorologists first collect the barometric pressure readings, usually measured in millibars and taken at hundreds of weather stations across the country. Each pressure reading is called the station pressure. So it's just, what does the barometer tell me the air pressure is? Then that number is adjusted to account for the elevation at the station where it was collected. Remember that air pressure drops with an increasing elevation, and without those adjustments, all the regions located at high elevations would be mapped as having low pressure. And locations below sea level, like Death Valley, California, would report high pressure readings. To compensate for altitude, all of the pressure measurements are converted to sea level equivalents. So we have a station reading, and we subtract a number of elevation so that we can figure out what it would be if this location where we are at Truckee, California, were in fact at sea level. And thankfully, it's pretty simple math. Generally, near the surface, pressure drops at about 1 millibar for every 10 meters of increased elevation, or about an inch of mercury for every 1,000 feet. This figure shows the adjusted air pressure values, usually referred to as corrected values, for 3 locations in California. So starting at the wharf in San Francisco, we're at sea level, and then start the climb up through Yosemite and all the way up to the top of the Sierra Nevada mountains. Because temperature also affects air density, and therefore the weight of the air column, temperature is also considered when altitude corrections are made. But the adjusted reading, considering both temperature and altitude, gives the atmospheric pressure as if it were taken at sea level under identical conditions. So normally the correction for temperature is comparatively small, so it's not included in the calculations shown here. Once corrected to sea level values, the pressure measurements are displayed on surface weather maps using isobars. ISO meaning equal and bar meaning barometric or pressure. Those are lines that connect places of equal air pressure. So you can see if we climb here, if we're at 1,008 millibars of pressure here at sea level, and we climb up 1,200 meters, I know that if I cross out the 0 under the Yosemite reading, I'm at 120 millibars. So I'm just dividing by 10, right, to get 120 millibars. So I know that I need to add 120 millibars to whatever I read at the station. Okay, so this happens to be 886, the reading at the station, plus the 120 millibar correction for altitude, brings us up to about 1,006 if the mountain wasn't there, right? So a slightly lower pressure. This is what's recorded on the weather map, okay? And that's for the 0, the sea level pressure level. Truckee, California, the same process. If I cross the last 0 off of 1,800 meters, I'm left with 180 millibars that I need to add to the station reading. So here's 824 plus 180. And that brings me a number really kind of similar to the other two that I've seen so far. So 1,004 millibars is just a little bit lower than the 1,006 we measured at Yosemite. This figure shows a simplified surface weather map. Notice that the isobars are drawn at 4 millibar intervals. So at 996, 1,000, 1,004, and so on. Closed isobars that roughly resemble circles identify high regions or low regions. The pressure in a high is greater than that of the surrounding air, and it's labeled with a large blue H. Whereas the pressure in a low region is lower than the surrounding air, and so it's labeled with a large red L. In general, high pressure systems are called anticyclones. They are associated with very dry conditions. The low pressure systems that occur in the mid-latitudes are called cyclones or mid-latitude cyclones to differentiate them from tropical ones. Tropical cyclones are also called hurricanes or typhoons depending on their intensity and location. But in contrast to anticyclones, which are those high pressure centers that are very dry, mid-latitude cyclones tend to produce stormy weather. The weather maps here, in addition to the isobars, show an idealized wind pattern with red arrows. Notice that the surface winds generally blow at an angle across the isobars away from the centers of high pressure and toward the centers of low pressure. In addition to surface maps, the National Weather Service produces weather charts that show atmospheric conditions at 850, 700, 500, 300, and 200 millibar levels. They do that twice a day, so every 12 hours. Remember that the upper air data comes mainly from radiosondes, instrument packages that are carried aloft by weather balloons. But of particular interest is the 500 millibar chart, showing the circulation of the atmosphere at roughly 5,600 meters, or 18,000 feet. Because the 500 millibar pressure level is in the middle of the atmosphere in terms of mass, about half of the air is below that level, and half of the atmosphere is above it. The 500 millibar chart is important because major weather systems tend to travel in the direction of the winds at that level. Like other upper air charts, the 500 millibar chart shown here shows variations in the height at which the 500 millibar level is found. Okay, so these lines, these constant lines, these ISO lines, are not the atmospheric pressure. They are the elevation of the 500 millibar surface. So rather than show variations in pressure at fixed heights, upper level charts are more like topographic maps. That is to say that the contour pattern reveals the hills and valleys of one constant pressure surface, in this case the 500 millibar surface. There's a simple relationship between height contours and isobars. Places that experience 500 millibar pressure at higher altitudes are subject to higher pressures than places where the height contours indicate lower altitudes. I know this is a complicated subject to chew on here. But in general, remember that higher elevation contours indicate high pressure. Lower elevation contours indicate lower pressures. Notice that the contour lines in the upper atmosphere chart on the right mainly consist of large sweeping curves labeled ridges and troughs. Ridges are elongated high pressure areas that extend toward the poles and are associated with warm, dry air. Troughs, on the other hand, are elongated areas of low pressure that extend equatorward, and they're usually associated with cool, wet weather. Use the course content provided on the Canvas site as well as outside internet sources to verify that you can formulate answers to these questions. If you can comfortably answer these questions, you are in great shape for the next test. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.